Hey guys, it is Mr. Van Low. Welcome to my YouTube channel. Do not click like, do not click subscribe. Okay, we're going to take a look at our final unit here, and it is organic chemistry. We're looking today at calorimetry. Okay, I'm going to be going fairly quickly because this is a video, and you can rewatch it as many times as you like. You will also have access to these slides if you would like to burnish your notes as you go. Okay, so if I'm going too fast, just feel free to rewatch the video, pause it when needed, slow things down as you like, or speed them up. It's entirely up to you. Okay, our goal today is to investigate the combustion of a fuel using a calorimeter experiment to determine the change in energy per unit mass of fuel. Well, unfortunately, we won't actually be doing the experiment, but we will see how you would go about it. So we'll be covering the theory here in this lesson. Okay, so temperature is the key factor when calculating heat transfer. Well, there are a few things as we'll see, but this is a big one. So the temperature variable is used, and the symbol that we use is just delta T. Okay, delta here in this context means change. So whenever you see that little triangle in front of a variable, that means change. So what delta T means then is change in temperature. So the more stuff we have, the more energy it can absorb and release. Makes sense, right? So what that tells us is that mass is related to heat transfer, and that mass is one of the variables, much like temperature, in our heat energy calculation. And mass will be symbolized by a lowercase m. We will see the complete equation here momentarily. As I said, I'm going to be moving fast, but you can pause if you need to. Okay. The specific heat capacity of a substance is the quantity of energy in joules required to change 1 gram of the substance by 1 degree Celsius. Note that in physics we use kilograms more than grams, and that just changes our specific heat capacity value by an order of 1,000. Okay, so it's not that tricky. So the specific heat capacity is going to be different for all substances, and it just tells you how well a substance can store energy. That's it. So if a substance has a large specific heat capacity, that means it will absorb and release more energy than a substance with a smaller specific heat capacity. So we use the symbol C for specific heat capacity. That is our variable. And the units for specific heat capacity are the joule per gram per degree Celsius. Okay, and that would look like this, as you will see later. Okay, there you go. Okay, next slide. Here we have specific heat capacities of various substances. You don't need to know all of these. Note that the most common one that we will be dealing with, though, is the specific heat capacity for water, which here is given as 4.184 joules per gram per degree Celsius. Okay, you can pause the video if you need to. I'm going to move on. You don't need to write all these down. This information would be given to you in a table or in a specific problem. There we go. Okay, so here is our formula. Q, heat energy, is given by mass times specific heat capacity times change in temperature. Okay, and our specific heat capacity depends on two things. It depends on what the substance is exactly, and it also depends on whether or not the substance is a solid, liquid, or gas. Okay. Note that our units are given here for all of our variables, which is handy information. Also note that our change in temperature could be in degrees Celsius or Kelvin. They are equivalent. So a change of 1 Kelvin is equal to a change of 1 degree Celsius. Okay, so here's an example problem. I have a coffee cup. It's full of about 250 grams of coffee. And at the beginning of the lesson, my coffee was nicely warmed up at 76.0 degrees Celsius. I forgot to drink my coffee, and at the end of the lesson, it had cooled down to room temperature about 22.4 degrees Celsius. So, question, how much heat was lost by the coffee? Well, how could we answer that question? Dun, dun, dun. There it is. Okay, so first thing we want to do is, of course, define our variables, as is always the case when doing these sorts of word problems. So, first thing you do, define your mass, 250 grams. Next thing we need to do is calculate change in temperature. And note that this is probably the only part of this topic where things can get potentially a little tricky. But if you follow my advice, it's going to be very straightforward. So here our change in temperature, and this is the standard way that a change in anything is calculated. Our change in temperature is given by the final temperature minus the initial temperature, okay? And this would be true of other stuff as well. So for example, if I had a different kind of problem and I had a change in mass, I would take my final mass and subtract my initial mass from it. This is the way we normally do that, okay? So in this case then, my change in temperature, my final temperature is 22.4 degrees Celsius. Remember, this is cooling down. My initial temperature is warmer at 76.0 degrees Celsius. So this is going to give me a negative value for change in temperature. And we'll see why that is useful momentarily. Okay, so my specific heat capacity was given in the table in a previous slide at 4.18 joules per gram per degree Celsius. Okay, we then plug our new variables, our newly defined variables, into the equation, and we find that the amount of energy here is negative 5.6 kilojoules. Now, recall from the previous lesson the significance of a positive or negative sign on energy. What does that tell us? Well, it tells us that this is an exothermic process, that my coffee is losing energy, right? So that makes sense, that it would be a negative value. Okay, so exothermic processes are negative energy. Endothermic processes are positive energy. Okay, so when we're dealing with calorimetry, we're going to be taking energy and putting it into water, okay? So that can be summarized as shown here. The heat lost by a process will be equal to the heat gained by the water. In other words, an exothermic process where energy is lost by the substances reacting will heat up water, which makes sense. So if you think of fire as an example of an exothermic process, we would expect that to heat up water, right? Okay, right. Next, heat gained by the process, an endothermic process, will result in cooling of our water. Okay, so let's be very explicit. So this would be exothermic. And this would be endothermic. Okay, the water gaining heat, that's going to be endothermic. The water losing heat, that will be exothermic, okay? So, Next slide. So here we have a diagram that would show a calorimeter, okay? So usually we see this in a kind of circular system. So imagine a styrofoam cup here. That would be the usual way that this is done. And if you look at Mr. Marier's notes, he shows a diagram of this process that I think you will find helpful. So we take a liquid and we put it in a styrofoam cup, and then we add to that styrofoam cup a couple of reactants. Okay, and a chemical reaction will occur. And we call that, this is referred to here as our chemical system. It could be two liquids, it could be a couple of solids placed into water, it could be a liquid and a solid. It doesn't really matter much here for our purposes. Okay, so if this process is exothermic, energy will go from the system into the water. So here, delta Q would be negative for the system, but positive for the water. So here we have an exothermic process. If energy goes from the water into the system, then our chemical system is endothermic. Okay? Remember, we're looking at what's happening to the chemical system, not what's happening to the water. We're measuring the temperature change of the water so we can calculate the energy going in and out of the chemical system. But our water is effectively a measuring tool. Okay, so here we have another example. We have a 70-gram sample of a metal heated to 95 degrees Celsius in a hot water bath. We then transfer our sample to a polystyrene container or a styrofoam cup. And this calorimeter contains 100 grams of water with a temperature of 19.8 degrees Celsius. The final temperature of the contents of the calorimeter was 22.6 degrees Celsius. And that value, 22.6, is very important because that's going to be the final temperature for both substances, the metal and, the 100 grams of water. Okay, so both of those will have a final temperature of 22.6 degrees Celsius. So, our question, how much heat did the metal lose? How much heat did the water gain? And next question, what is the specific heat capacity of the metal? Okay, so here we have a very important concept. First, the amount of heating that occurred, okay, so the amount of heating that the water experienced is equal to the amount of cooling that the metal experienced, okay? So the energy transfer is equal between the metal and the water, okay? So this is a very, very, very important concept. So we can calculate the heating of the water very easily by using our previous formula and defining our variables. So we know that we have 100 grams of water. We know that it has a specific heat capacity of 4.18 joules per gram per degree Celsius. And we're going to calculate our change in temperature. Now, this is the important thing. This value must be positive. So a change in heating temperature has to be positive. Okay, so your initial and final temperature, in this case, are going to be flipped around. Okay, so this will give us a positive value for our heating substance. Okay, and that value is given by 1,170 joules. Okay. Our cooling substance is going to have a negative sign. Okay, so that's what we see here. And remember, we're just looking at endothermic and exothermic processes. So the water is heating up, that is endothermic. The metal is cooling down, That is exothermic. Okay. So there's the first part. The second part, B, what is the specific heat capacity of the metal? Okay, so here we have to rearrange our equation, Q equals mc delta T. We have to solve that equation for C, which I've done here. Okay, we then plug in our values. And in this case, our change in temperature needs to be negative because what we have here is a system that is cooling. Wait a minute. Yeah, cooling. Yeah. Okay. So our cooling system then is illustrated here with our negative change in temperature. And we then plug in our values and finish our final calculation there. Okay, there we go. That is it. No, it's not it. Okay, we have one more example problem. Many homes in North America use natural gas for heating and water heating. So, like calorimeters, natural gas water heaters have an insulated container filled with water. So a gas flame at the bottom heats the water. And a typical water heater might hold 151 liters of water. So our question is, how much thermal energy is needed to raise the temperature of 151 liters of water from 20.5 degrees Celsius to 65 degrees Celsius? So we're going to be making the same assumptions that we made for our calorimeters. B, if it takes us 506 grams of methane to heat this water, what is the heat of combustion of methane per gram? Okay, so let's answer our first question. First, we define our variables, and we know that the specific heat capacity of water is 4.18 joules per gram per degree Celsius. Our mass of water is given by 151 liters times 1 kilogram divided by 1 liter. So there's our conversion factor. And you guys will recall that from earlier topics. Okay, we have here a problem though because our units of mass do not agree with each other. So we need to convert this mass to grams. Okay, so I've done that then by multiplying by 1,000. What I get then is 151,000 grams. Next, we look at our change in temperature, and our change in temperature is going to be equal to 44.5 degrees Celsius. And this would be positive because we are heating water. Okay, so we then calculate our energy, and we find that it's 2.81 times 10 to the 7 joules. And our heat of combustion per gram of methane is just equal to the energy that we have used to heat the water divided by the mass of methane. Okay, so very straightforward. So we take our previous value, 2.81 times 10 to the 7 joules, and divide by 506 grams. And that then will give us a value of 5.5 times 10 to the 4 joules per gram. And you could easily check this by jumping onto the internet and looking up the heat of combustion per gram of methane. And I advise you to do that now. I am pretty sure I'm done. Yes, I am done. Okay, so have a great day, and I will talk to you guys soon. Bye.